I just want to set up with an overview of what I'm going to talk about. So first thing I'd like to point out is where bandwidth, network bandwidth has gone in the last couple of decades. So the first system I worked on, very new to my career, was the Red Storm system. It had an amazing, at the time, 1.1 gigabytes per second per direction of network bandwidth. And the most recent system I worked on is Frontier, and it has 100 gigabytes per second per direction of bandwidth. And if I told you that, in 10 years, your commute was going to get 100 times faster, you would think that was amazing. Until I told you that you had to commute 40,000 times as far. And then it wouldn't be so cool anymore. And that's kind of what's happened with the compute side of the platform. So we went from a 4 gigaflop node, a very lovely 4 gigaflop node, single CPU, single core, yes, it was that long ago, to a 180 teraflop peak rated node, 45,000x in one node with 100 times the network bandwidth. So that's going to have some real implications for what you're going to have to do. There's other things going on in networks. So global bandwidth is expensive. Now that got a little bit better. We got kind of a one-time shot at that with improvements in technology and some other underlying changes. We went from torus networks were kind of the norm in 2005. So Red Storm, the XT3 platform, all the way up through the XK platform were all torus networks. Blue Gene was a torus network. There were lots of torus networks out there. And then we kind of got to the point where it was no longer so easy to build a torus network. I'll talk about that in a little bit. And so we got a one-time topology change. And that's given us a bigger boost in bisection bandwidth relative to injection than we had back then, but that's not going to change again. Transistors are cheap. I don't know if you've looked around, but all these parts now have lots and lots of transistors. That's a good thing. Building new chips is not cheap. Really, really, really not cheap. That's putting pressure on us. But the good news is when you build one, you can put new features in to help optimize the network to hopefully cover some of this gap. Right? This is a big gap that's developed in terms of compute versus communicate ratio, and so we have to work harder. Another interesting thing that's happening is that supercomputer networks are converging with the data center networks. If you look back just a few years, every supercomputing network was a one-off. It never plugged into anything but itself, and it had to bridge out into the data center. If you needed to get an instrument, it was over there, and that is starting to change. Okay, so some things that I will harp on through this talk. Locality matters a lot more now. You need to communicate less. You need to find a way to keep those communications local and on node. You need to program for overlap. I will probably say this at least 3 or 4 times. I might say it 3 or 4 dozen times because in the old day, people would write applications and they would communicate and they would compute and they would communicate and they would compute, and never the two would overlap. And you go to the application developers and say, there's this opportunity here. We built this really nice network. It can overlap compute and communication. And they would say, yeah, but that's hard. I will tell you it's a lot harder to rewrite the rules of physics than it is to overlap your compute and communication. So that is something that we need you as developers to do differently going forward. And we'll talk some more about that. And then the future, we're going to see the ability to communicate more directly with the instruments over distances. And I'll talk about that just briefly in a slide here in a minute. Now, one of the things I did not want to do is stand up here and give you a Slingshot marketing talk. And so the first thing I did was put in a Slingshot marketing slide. But this slide has a point. So the point of this slide is that as we're converging the networks, if we look back in the old days, the supercomputer networks were one-offs. They never connected to anything. They were completely proprietary. You re-engineered it every single time. Every chip had a completely different interface, different network topology potentially, different signaling. You never plugged two together. And that wasn't good. Now there were good things. They were low latency, they were high message rate, they were high bandwidth. Okay? They were scalable networks, they were reliable networks, those were good things. If you looked at Ethernet networks, they were literally everywhere. You could plug a Ethernet network into your printer, into your laptop, into your supercomputer to run your storage system. They were everywhere. There were lots of vendors. Big ecosystem. Big ecosystems are good. They help bring down costs, or at least contain costs these days. But they weren't really that efficient. they were high latency, they were lossy, they didn't care that much about reliability. I saw a great talk once where somebody wrote to disk and read back from disk over the course of 3 weeks and just did that repeatedly, and talked about how many hundreds of silent data corruptions they detected, partially because they were running that data over the network, and when it passed through standard Ethernet switches, nobody cared. And so there were literally a few hundred bit flips in the data that nobody detected. So we brought those things together into Slingshot. And so that one of the things that puts on the horizon is this vision of going from the edge to the EXASCALE. So Cray's been building, and now Cray, part of HPE, has been building supercomputers for a long time, okay? And with Slingshot, we have a really nice supercomputer network. It's in Frontier, it's going to be in Aurora, it's going to be in El Capitan. It's a really nice network. But one of the interesting things about it is that it's Ethernet, which means that it can bridge straight into the data center network. You can plug one end of it into the data center network, nice cable in between, no clunky routers, none of that. And so there's this vision in the future of being able to extend that out and to reach out to instruments and to be doing filtering and processing of the instrument and bring that into a supercomputer real time. It's an interesting and cool vision. We're not quite there yet, but when you look at this, the facilities that are out there and the types of experiments they're running, that is on the horizon. Now I want to just give you a sense of the scale of an EXASCALE network. So the Frontier network has 2,300 management agents. Those are little processors connected by their own network. There's like this little supercomputer running the supercomputer in the back side of it to go out and provision it and do discovery and program up the switches. If you look on the right-hand side, it goes into some details about the rest of the fabric. It's 9,400 compute nodes. Each of them has 4 NICs. That gives you 37,000 plus NICs, 18,000 L0 cables, 9,000 L1 cables. It's a lot of components, guys. And that's why it's a lot of work to get the first one of these up. There's a lot of components, and when you buy whole truckloads, literally, of components and bring them in and plug them in, some of them don't work. And the Aurora fabric is going to be even bigger. I think you said 9,000 something nodes and 8 endpoints a node, so it's twice that. So in terms of the part of the network that most of you would interact with when programming the system, it's the NIC. And so Cassini is our NIC for Slingshot. There's a very nice die photo on the right. We hardware people get really excited about die photos. You may not care at all, but we get really excited about them. It's kind of interesting because there's 2 NICs in that die. That is strictly a packaging optimization, nothing else. It was easier to build the system by putting 2 NICs on one die and packaging it up that way than by not. So that gives you 2 200 gigabit links out of one package, 2 PCI Express Gen 4 interfaces as the host. Now we actually support extended speed mode, which is kind of interesting. There's this weird quirky little definition that was related to C6 back when C6 was going to be a thing, but it's not anymore, where you could run the links at up to like 25 gigatransfers instead of the standard 16. Cassini provides a wide range of HPC offloads, so we'll actually do MPI tag matching in hardware. We'll give full independent progress. For those of you who are new to MPI, there's been this long-standing debate in MPI about whether or not you had to give full independent progress. Full independent progress just means that if 2 sides, one calls send, one calls receive, and then they go off and do something like dgem for half an hour, and they come back, the message should have completed while they were off doing other work. With a lot of networks over time, that has not been true. We offload both eager and rendezvous transfers. This is something else that's relatively unique to Cassini. We do the tag matching for both expected and unexpected messages. Also a little bit unique to Cassini. The other interesting thing on this slide is that it's also Ethernet. So over the same wire, it also runs Ethernet, and it plugs into all the same Ethernet stacks in the kernel. So it plugs in right in the bottom of the IP stack. It does some of the standard offloads. No, it's not a full TCP offload engine, for those of you who remember those, but it does plug into things like GSO and GRO offload engines that are in the Linux kernel. Another important piece of the network technology stack that doesn't get talked about a lot is the network API. libfabric is the network API that we export. It's relatively new, and it's multi-vendor. And the multi-vendor part is actually pretty novel in HPC. Historically, every time somebody put out a new supercomputer network, they would drop a new network API on you and a new MPI over top of that new network API, and it would take a while to shake them both out together. LibFabric is kind of here to stay. It's going to evolve with time, right, as the networks add new features, but it's kind of here to stay. It's what we intend to support for the foreseeable future. It was actually born at Intel. While I was at Intel, we were building a NIC that was based on Portals 4, and they said, well, we need a community API to expose, and so we went off and created LibFabric. Largely exposing the same feature set as Portals 4, and heavily influenced by the PSM API that was being done there at the time as part of the OmniPath program. LibFabric now ships from HPE, from Amazon and AWS over top of their EFA, from Cornelis Networks over there. They picked up OmniPath, and I think there's a couple of others out there that ship some portion of it. This API exposes traditionally PGAS things, RMA things like put/get, two-sided operations, including matching, atomic operations, something we call triggered operations, and a locally managed offset semantic. Now let's look at a node architecture. I used a frontier node architecture because when I asked to use a picture of the Aurora node architecture, nobody responded. And so you saw one of those in the other talk. Here's frontier node architecture. Interesting aspect of this is that we've got these NICs under here, and if you'll note, the thing they connect to is the GPU. So they sit underneath the GPU. The CPU is actually kind of over there. You can actually see that when you do benchmarking runs on it because the CPU is kind of over there. But there's locality in here that you have to worry about, right? And there's affinity between the NUMA domains in the processor and the GPUs that are hooked to it and the NICs that are hooked to those. Now Aurora is different. The NICs in Aurora hook underneath the PCIe switch. You saw that in this picture. Then they go into the processor, and the GPUs hang underneath that processor. Also, there are 8 NICs and 6 GPUs. So something that until we lived a lot of years where supercomputer architecture was a processor and a NIC and a fabric behind it. And that was pretty simple, relatively speaking. We're now in this world where you might have 4 GPUs and 4 NICs, or you might have 6 GPUs and 8 NICs, and that's a little bit different to think about every time you touch a different thing. The NIC might be attached to the GPU, or the NIC might be attached to something else. It's a little bit different thing to think about. There's going to be optimizations of the way you set up your problem and the way you run your problem on each of these systems if you really want to get the most out of them. All right, I suspect I'm running a little bit long. So topologies are driven by technology. So we went from torus topologies to higher radix topologies because when we got to the point where torus topologies had to have optics, they were no longer inherently better. Basically, when the optical cables got too short to wire torus, and you're going to have to drive optics anyway, it was time to look for something else. And so modern topologies use the fact that they're already going to go optics to optimize the bisection bandwidth of the system. But be aware that topology still matters and locality still matters, and we will all tell you, us included, about how great our topology is at handling your workload no matter how you lay it out on the system. But you can always get a little bit more by understanding what you're doing and how you lay your problem out on the system, because it affects how that problem loads the network. So one topology you'll encounter, now that we've moved beyond toruses in general, is a fat tree. You'll see these in fully provisioned and tapered versions in the systems that are out there in the field today. Fat trees are layered networks, and so some things are near and some things are up the network and back down. If they're not tapered, then they're in theory non-blocking. In practice, that's not quite how that works out because of routing constraints. If they are tapered, as you go up the layers of the tree, you have less bandwidth, and so you have to be very careful about contention across those upper layers. In Frontier and Aurora and El Capitan, there will be variations on a Dragonfly network. Dragonflies are all-to-all connected in a group. Well, people like to generalize the term Dragonfly, but the canonical definition and what's built in those systems. They're all connected in a group of switches, and then each of those groups is all-to-all connected to the other groups. And so that's what you see drawn here. So you've got this notion, do I have a pointer? Yeah, there we go. You've got this notion of a group where it's all-to-all connected between the switches, and then each of these boxes here is another group, and the groups themselves are all connected between them. Dragonflies can also be tapered or not, just depending on how you build it. They scale much better for unit cost than fat trees do. And so when you start talking about networks that are tens of thousands of endpoints, it's cheaper to build a Dragonfly than to build a fat tree, and you get comparable levels of global bandwidth. Now, one trick is that you have to have some fairly sophisticated adaptive routing here, or these networks have some very ugly corners. And so one of the things that Cray and HPE have spent a long time developing is adaptive routing. And so we're on like our 8th generation of adaptive routing in the Slingshot network. So just a few features. I said at the outset that we're going to have to do more in terms of features in the network to help make up for the fact that we don't have the bandwidth that we used to have. So things that are going to matter are things like adaptive routing, where per packet we can make a decision about how we're going to route through the network to get around contention that might have developed because of the way the application loads on the machine and the way they contend for global links. There are quality of service classes that will allow us to do things like prioritize different flows based on the type of traffic they are. And so an application might have access to 2 or 3 quality of service levels. If it has something that is short and high priority, it can be given more priority in the network. But then you have to do things like, well, for that high priority thing, we better turn down its bandwidth that's available because you don't really want a high priority thing being able to consume all the bandwidth. And then there's congestion management. A lot of effort was spent in Slingshot on congestion management. In the old days, every time you ran something on a system, it would probably get a little bit different performance. And the reason for that was there was other stuff running on the system. And what else was running on the system had a huge impact on how your application ran when it was on the system. And so Slingshot put a lot of effort into building congestion management that's capable of reducing that interference between applications. And so the lowest tech slide we could provide showing that example is run from Frontier. There are three boxes here. Top left is we ran these things on an uncontended system. No other congestors. Bottom left is, okay, some of the system was running these tests. Some of the system was running like congesting workloads. And so there's some ugly congesting workloads in the set. And then the bottom right is the ratios. And what's important, if you look to this bottom right, is that the average and tail latencies don't really go up as you load congestion onto the system. And that's what helps reduce that interference in the network. That's evidence that we've reduced that interference in the network. And that's kind of what we have to achieve if we're going to live in these environments where the compute has grown 40,000x and the bandwidth has grown 100x. Okay, so now I want to talk for a little bit about what the hardware needs from you, because there's lots of things we can do in the hardware to make things better, like congestion management. The fact that you don't need to over-provision your bandwidth so that multiple apps can run at the same time and not interfere with each other, that saves you a lot on your bandwidth bill. But we can't do everything, right? There's some stuff that we need you to do, like facilitating overlap. Now, I made this comment before about how apps used to just compute and then communicate. And so the communication would sit there idle, literally idle, for 90% of the time sometimes, right? Because if an app spent more than 10% of the time communicating, it wouldn't scale. And so they'd compute for 90, communicate for 10, and repeat. If you can overlap your communication behind your computation, then that communication time part of the application reduces, which is good because otherwise it would be increasing because your amount of compute you're doing is drastically shrinking your problem computation side. So what this means is that you need to use non-blocking sends and receives, and you need to schedule the communication relative to the work. okay? So you need to find the parts of the communication you can do while you're doing something else, because that's how you hide the communication time. There's a real-world example recently working through frontier applications. It was not using overlap effectively. They went in and they did some surgery on the code. They moved around the communication calls, and they moved around the way the work was scheduled and got rid of big idle gaps in the network. And those idle gaps were really cutting into their performance. They got a big performance boost out of getting that. And so the right hand side over here is an example of what that looks like, which is post your receive, do some work that doesn't depend on it, post another receive, and do the sends that are the result of that phase, because many applications have some kinds of phases in them, right, where you can schedule your work like this. Now, I didn't put any waits in this. Waits are dangerous things. Basically, you don't want to wait until you actually have a data dependency, because when you wait, it goes out there and it waits until stuff is done. And so if you're waiting for it to be done, if you call wait before the communication is actually done, it means you're going to go wait until it's done. And so that's time that you're not overlapping computation and communication. Please use expected messages. So the notion of an expected message is that you have posted receive before the message has gotten there. And I will confess that this is hard. And I don't expect 100% success all the time, because it's hard, right? But it's important, because unexpected messages mean that you're going through more software on the target side. You're copying data. The way MPI messaging works is normally there's some eager portion of the message that you start pushing across the network. And if it's a big message, you push part and the other side pulls part as a rendezvous operation. And so that part you pushed, you want to catch it, because otherwise that's completely wasted and you have to throw it away and you have to try again, right? And so you put something to catch it. Well, when you catch it, you don't catch it in the buffer the user wants it to be in, because it was unexpected. And so you catch it in a system buffer somewhere. And so then the software has to copy it from wherever it landed to where the user wanted it when the user later calls receive or when they call wait, okay? We ran into this on Frontier. We had an app that was fairly sensitive to message rate and fairly sensitive to latency, and it was having a bunch of unexpected messages, and that drives them both up. And so they pulled their receives up to the top of the code, and voila, the unexpected messages went away, and the application performance went up substantially. Now, I put something in here. All this is pseudocode, obviously, because, well, partially because a real MPI call with all of its arguments wouldn't fit on the screen, but partially because I didn't want to bother with all the arguments. But I put something in the pseudocode to make a point, which is you may need to double buffer to make this work. You may need to set up a receive into one buffer and do work on another, right? And so you may have two copies of where you receive into in order to make this work, just because of the scheduling. You need to post to receive way up here, right? And maybe not wait on it until way down here, and maybe in between you had some work you needed to do where that buffer was going to be. So you may have some bubble buffering that has to be done to achieve that. People have done that before. I've seen codes do it, where they had faces of matrices that they exposed, and then they would toggle the pointer. So they would have two copies of the face. They would receive into one while they were working on the other, and then they would flip the pointer the next time they went through the loop so they could receive into the other while they worked on one. It can be done. It is a pain. I'm not going to deny that, but we do need some exposure of overlap. Do express concurrency. So these systems, you've got 4 or maybe 8 NICs. The problem with 4 or 8 NICs is that, generally speaking, you're not going to split one message across them. So if you're not going to split one message across them, that means if you only send one message, you're only going to use one NIC. And that's going to waste a whole bunch of your bandwidth. So do express enough concurrency. There's other slides where, if I get the chance to make the point, I will point out how you actually need even more concurrency, because you need more cores driving the network depending on your message size. Actually, there's a little bit of discussion here. The problem is that one core can only drive the network so hard in terms of message rate. And so And if exposing concurrency means your message gets too small, you'll need to have more cores to actually achieve that. Okay, more cores that are actually doing the communication phase of the app. And I went through some example calculations here, but it's not that relevant, except to say you got trade-offs to make. But if you don't expose enough concurrency, there's nothing we can do, right? There's a finite rate at which the cores can drive the network. We're working to improve the rate at which cores can drive the network by making software overhead lower and lower, but there's only so low that it's going to go. There are alternatives, like there are some newer collectives, newer like MPI3, newer, but there's some newer collectives that it lets you express a lot more to the underlying implementation in one call. There's some new partition communications came in at MPI4. They're kind of interesting in that they are intended to make it easier for you to express more concurrency, express when more things, make it lighter weight to say, hey, this part of the message is ready to send, and by doing that, allow you to drive the network harder with smaller messages. Now, I will caution you that the newest MPI features tend to have a chicken and egg problem. That is, until somebody uses them in an application, the implementers don't spend a lot of time optimizing them, or until they show up in a procurement requirement, the implementers don't spend a lot of time optimizing. But work with your vendor. Like if there's something that really works for your application, right? Use it, and if it's a problem, talk with your vendor because a lot of these things can be optimized. Now, okay, so I've got some don'ts in here as well, which is don't overwhelm your NIC resources. So when the NIC decides that it's going to do something nice for you like offload matching, it reduces your software overhead. It gives you this nice independent progress capability that allows you to overlap, compute, and communicate. But it means that pieces of MPI are now residing down on the NIC. And one piece of MPI is this notion of a posted receive queue and an unexpected message queue. And these are typically implemented as linked lists because that's what's easy, but it's also because there's some ordering constraints in MPI that make it harder to do other things. When those lists get long, you start talking about traversing a long list, a long linked list traversal. I'm sure all of you are experienced enough to know that traversing a long linked list takes time. And if you do that every time you post or receive, or every time you receive a message, that is not what you want to do. So there's some work to be done to make sure that you don't get, thousands of things sitting down there in the NIC because it's got finite resources. This is just a slide to highlight one of the things we focused on in CASSINI, which is tolerating longer lists. There's a whole bunch of message rate benchmarks you'll see historically where they benchmark the network by always hitting at the head of a linked list. And that's great, but it's not real, right? If you post your receives to try to get all the overlap you can get, you're not always going to hit at the head of the linked list. And so this is just where we've done some benchmarking saying, okay, up to, in this case, up to about 64 entries deep, there's no hit on our message rate for depth of traversal into the list. Now, this also highlights the bottom line here is 16 ppn. The top one is 64 ppn. This just highlights it takes more cores to drive the network. These are all small messages, like 8-byte messages, that were run in these tests on the left-hand side. Okay, don't program an incast. Please don't program an incast. What the network is designed to do is to manage an incast so that if you do program an incast, you don't hurt the other people running on the system with you. Okay? There are actually vendors we've talked to in the past, like cloud service providers who have said things like, well, really what we want to know from the network is who has programmed an incast so we can kill their job and go tell them to rewrite it. There's nothing we can do about the time that you waste sitting around waiting for an incast to complete. If you send 100 gigabytes to one node and everybody sits there waiting for it to be done, it's going to wait until that's done. And that's what your app's going to do. And there's nothing we can do about that. Okay, people routinely do this, unfortunately. Comes up all the time, and then they have to go back and try to fix it. But if you think about it, if you've got 1 million ranks in your job and you post 1 million receives, what happens if the one that comes in is 1 millionth, right? You walk 1 million entry linked list. That's not good on any platform ever. One side note comes up talking about this. If you want to use MPI any tag in any source, that's fine. Either like use them both and always use them in the application, which is not the right thing for most applications, but there are like parallel discrete event simulation that works great for. Most applications that's not. Or never use them, because as we evolve the network, we're trying to do things to deal with the fact that these lists can go kind of long. We want to put in a hash table. If the field you have to hash on is star, you look at it and go, how do I hash any? And you kind of can't, and so that kind of breaks things. All right, just some congestion management results from Slingshot. This gives an example of with and without congestion management, without on top, with on bottom. You can see the total time the solution gets shorter on bottom because we've dealt with this green congester line and kept it from harming the other users in the system. I'm running out of time, so I'm going to skip through that. All right. Don't use unscalable constructs. So there once was an application that was a Monte Carlo simulation, and they computed all the partial results, and then they did an MPI gather to get all their partial results to the root, and then they summed them all up. And they couldn't figure out why, 100 nodes, they were scaling okay, and by like 1,000 nodes, it was because they were gathering to the root a really large amount of bandwidth. And by the time you gather, 10 gigabytes onto a node with a gigabyte per second network, that's going to take 10 seconds. And your app's going to sit there while it does that. So don't do that. It turned out MPI reduce was the right answer in that case. There are more scalable constructs out there. So there are one-sided operations, an MPI3 RMA, and OpenSHMEM has another API that's out there that allows you to get one-sided things. This is not a panacea, but it does get rid of the notion of traversing a linked list. But you lose the inherent synchronization that's in MPI. So MPI gives you two-sided operations with inherent synchronization. You receive, the other person sent when your receive completes. And so it lets you manage access to your buffer, and you have to do all that yourself when you're programming one-sided things. So if you need to do complicated things where everybody talks to everybody and 1 million people talk to 1 million people, PGAS kinds of things may be a better answer for you than posting 1 million receives. Okay? If you're talking to a few people, two-sided operations may be a better answer. Talk again about partition communications, and I'll wrap it up here. I'll skip my comments on the fads. So, all right. Point of the talk is that as the ratio of compute to communicate has gone way up into the stratosphere, the network's having to be smarter. All right? We can't just throw raw bandwidth at it anymore. The cloud service providers have run into the same thing. Right? For a long time, what they did was throw raw bandwidth at it to deal with the fact that TCP was not a great congestion management or high throughput solution. And so they just throw raw bandwidth at it. And they found they couldn't afford to throw raw bandwidth in it anymore. And so congestion management became an important part of their world. It was kind of important part of ours to improve the throughput of applications when there's multiple applications running. Do get out there and use those features that we're building. All right, use the overlap that we're giving you because that's how you're going to continue to get high application performance in the presence of low raw bandwidth relative to your compute. All right, I'll stop there because I know I took up some bonus time.
Thank you. You did a very good job putting us back to schedule.
I try.
Yes, you did. You tried. Any questions?
Go ahead. You mentioned don't use wait all or that it might not help. Is there a overhead associated with many wait calls versus a wait all?
Not a lot. There can be some. Like a wait all lets you go, depends on how the implementation has chosen to optimize around it. And if you do individual weights, none of which are done, then it doesn't do you any good to do individual weights, right? It's all about making sure you don't wait until you need to because you've got a data dependency.
Yes, please.
Yeah, I guess you listed a bunch of ways where the programmer can kind of shoot themselves in the foot. Are there future extensions that you think should be in the standard to help avoid these situations, and are there things that you're working on in the short term to help the programmer?
I haven't engaged with the forum a lot real recently. Partition communication was the last thing I was involved with, and that was one of those things to help the programmer. MPI in the forum will routinely say among themselves, we don't stop a user from shooting themselves in the foot because sometimes productivity is more important, right? Sometimes getting the application coded. Sometimes you're coding an app that's only ever going to run on 16 nodes. And so a lot of these scalability things don't matter. My favorite quote from the MPI forum was when we were arguing about something and somebody made the comment that, yes, we always say the user is allowed to shoot themselves in the foot, but I think what Keith is saying is that we don't want to hand them a hand grenade vending machine. And the image of an MPI call is a hand grenade vending machine, just as always. Right.
No more questions? Thank you. Thank you.